Good morning. My name is David Pridmore, and I'm presenting Reducing Furnace Operating Cost, How IGBT MFDC Technology Saves Energy. I am a sales application engineer for RoMan Manufacturing. I have a bachelor's degree in chemistry and math and have grown up in the lab. I transitioned to a sales application role where I now apply my experience with the scientific method to new products and technology. I work for RoMan Manufacturing, located in Grand Rapids, Michigan. We specialize in water-cooled transformers and power supplies. In this presentation, we will be examining power characteristics of the IGBT MFDC power system. The IGBT portion stands for Insulated Gate Bipolar Transistor. This is the control portion. MFDC stands for Mid-Frequency Direct Current. This is the high current transformer portion of the power system. The IGBT MFDC power supply can be used in place of SCR and VRT power controls. Some of the benefits that IGBT MFDC offers are less kilowatt usage, lower peak demand, and better power factor when compared to other power controls. In order to evaluate the IGBT MFDC power system, we're going to go over a case study in which we performed a retrofit of a vacuum furnace powered by a VRT. We directly compared the power characteristics of the two power supplies. From this case study, we will demonstrate a 40% reduction in kilowatt consumption, a 14% reduction in peak demand, and a high displacement power factor throughout the cycle. All of this results in lower cost for furnace operation. Here, you can see the details to the vacuum furnace retrofit. On the left, we have the VRT and vacuum furnace as it was originally built. The furnace VRT was rated at 645 kVA. There were 20-foot water-cooled cables that went from the VRT to the power feed-throughs on top of the furnace. It took approximately 1 week to remove the VRT and place the IGBT MFDC system, which you can see here on the right. A couple things I want to point out here. One is that the MFDC transformers are located on top of the furnace near the power feed-throughs. This is an important part of the IGBT MFDC value proposition that I'll get into later, but please take note of that. The second point is that this retrofit provided a very good comparison of the two types of power supplies. Most components in this retrofit did not change. We used the same furnace and the same heating elements. In order to compare the two power supplies, we ran the cycle shown here. We ran at a heating rate of 10 degrees Fahrenheit per minute up to a soak phase of approximately 1900 degrees Fahrenheit. We ran this cycle on the VRT and then ran a similar cycle on the IGBT MFDC system. We then measured upstream three-phase power characteristics at the main breaker that went directly to the heating power supply. We then characterized these two phases of operation in terms of power. First, we looked at the ramp rate phase, and then we looked at the soak phase. Before I get into the results of the case study, I want to go over some basic definitions of power. Real power, or kilowatts, is usable electricity. Reactive power, or kVAR, is wasted electricity. On the right here, you can see the power triangle. Real power is on the bottom and is 90 degrees out of phase from the reactive power, or kVAR, on the right. The angle that this triangle forms is known as the displacement power factor. I'm going to get into this more later, but it is essentially how the current can lag from the applied voltage. There are three components that we looked at during this case study. One is the total kilowatt hours, which is a billable quantity, the peak demand, which is the most amount of current drawn and has associated penalties, and the displacement power factor, which can make energy more expensive. Here are the results for the case study. First, let's look at kilowatts. The graph here shows a comparison of kilowatt usage of the VRT versus the IGBT MFDC power supply. Let's break down this graph. On the left y-axis, we show the real power measured in kilowatts. On the right, we have a secondary y-axis that shows the temperature in degrees Fahrenheit. This blue area is what was shown on the previous slide, where the furnace ramps up to a 1900 degree Fahrenheit soak phase. The two lines represent the kilowatt usage of the VRT and the IGBT MFDC power supply. This trend is what we expected to see. As the furnace is ramping up in temperature, it's going to take more energy, and at higher rates, the higher temperature you are at. And then when the furnace gets to a soak phase, the energy requirement drops to a plateau because we're simply maintaining heat. In this case study, we identified a 40% reduction in total real power consumption, or kilowatts, when comparing the two power supplies. Next, let's examine the peak demand, or the highest instantaneous current that's used for the process. This graph is similar to the last slide, where you have the heat treat cycle in blue in the soak phase at 1900 degrees Fahrenheit. The left y-axis is now amperage or current. Again, you can see the trend of increasing current during the ramp phase and then a plateau phase of energy requirement. Within the circles on the graph, you can see the peak current draw. We identified a 14% reduction from the VRT to the IGBT MFDC power supply. This correlates to lower peak demand charges for the furnace. This also offers the furnace operator the ability to change the ramp rate. The furnace can get up to heat faster for that same peak demand, making the furnace more productive. Or, conversely, the operator can focus on peak demand and reduce that throughout the facility. The reason why we see a lower peak demand is that the control, which I'll get into later, rectifies the three-phase 480 volts upstream to 650 volts out of the control. This higher starting voltage allows us to step down the voltage further within the transformer, which results in a lower primary current draw throughout the entire system. Finally, let's examine the displacement power factor. This graph is similar to the previous two, but on the left y-axis, we're looking at displacement power factor. A good displacement power factor is close to 1. That means that power is being delivered most efficiently to your system. As a power factor gets lower, it can incur penalties and other complications for the facility. This is why some customers will use a capacitor bank in the facility for correction. You can see that with the IGBT MFDC power supply, the power factor remains near unity throughout the entire cycle. If you were to compare this to a phase angle control, as the power drops down and we go to a lower set point, you would see a lower power factor. One thing I want to point out here is that we matched our system to the 645 kVA VRT. During this cycle, the IGBT MFDC system never exceeded 300 kVA. So, at its maximum operating point, it was still 48% of the total capacity. It was even lower than that during most of the cycle. The take-home point is that the IGBT MFDC power supply has a very good displacement power factor at any practical set point. In this slide, we're going to look at kilowatt usage more closely. These graphs are similar to the first graph I showed you, where the left y-axis is kilowatt usage, and the x-axis on the bottom is total time. If you integrate the kilowatts used over time, you get to the billable quantity of kilowatt hours. The difference between the VRT and the IGBT MFDC system was approximately 194 kilowatt hours. This equates to a savings of 38 kilowatts per hour of use for this furnace. If the furnace was used for 20 hours a day over the course of a year, the IGBT MFDC power supply could provide savings of up to $28,000 from kilowatt savings alone. This doesn't even take into account some of the other factors that could improve savings, such as power factor improvement, lower peak demand, and increased productivity from ramp rate adjustments. How does all this work? Here we have an IGBT MFDC pictorial schematic. Let's start on the left side. The input into the system is 3-phase 60 Hz AC. We show 480 volts here, but other main voltages can be used. Within the control, the power is first rectified into 650 volts single phase. It is then smoothed over with a capacitor and inverted with the IGBT into mid-frequency. The output of the control is 650 volts at 1000 Hz. This is distributed to the MFDC transformer and stepped down to low voltage, high current power. Within the MFDC transformer, there are diodes that then rectify the mid-frequency AC waveform into high amperage direct current output. This DC current is then delivered to the load or whatever heating process you are using. Now, let's get into some of the theory of why this is so much more efficient. Let's start with the first point, which is DC output is better. With DC output, there's no inductive reactance. If you look at the triangles here, on the left we have Ohm's law, described visually, and on the right we have the impedance triangle. With AC output, when you consider the impedance triangle, we not only have the resistance of the circuit, but also the additive reactance. Reactance adds more impedance to the circuit, and it is a function of the AC waveform as well as the physical area within the secondary circuit. AC has more resistance in the form of impedance because you have more of that inductive reactance. By using DC output, we reduce the resistance or impedance of the system, and this means less energy is being consumed outside of the heating zone. This also goes back to the initial description of close coupling the MFDC transformers to the power feed-throughs on top of the furnace. That very short secondary circuit reduces resistance, which reduces unnecessary losses outside of your heating zone. On to the second point. The IGBT MFDC system uses shortened secondary cables. I touched on this on the last slide, but I want to go into the physics of it here more on this slide. On the left, you can see Joule's law, which shows that heat is exponentially proportional to current and directly proportional to resistance. By Ohm's law, we know that current and resistance are inversely proportional to each other. So, if we can reduce resistance in the circuit, we can increase the current through the heating elements, which makes heating more efficient. By reducing the length of the secondary cables, we have less losses through less resistance getting to those power feed-throughs. The third source of efficiency is inductive shielding. So what is inductive shielding? The graphic here shows how current can lag from the applied voltage. This is dependent on how much inductance you have in the system. An ideal power factor is 1, or unity, when the current waveform is directly over the voltage waveform. With the IGBT MFDC control, with the rectification, capacitance, and inversion, the upstream circuit, or what the power company sees, is shielded from the inductive heating element side. This is how the IGBT MFDC system has a displacement power factor of near unity at any practical set point. The fourth source of efficiency in the IGBT MFDC system is the DC heating pattern. Simply put, a DC heating pattern is better than an AC heating pattern. The graph on the left shows the heating pattern of alternating current. The heating pattern of alternating current changes from 0 to its maximum during each half cycle of the frequency. This reduces the quality of the heat due to the large variance in instantaneous current to the process. The DC waveform, shown on the right, demonstrates a more stable heating pattern and makes heating more efficient. In conclusion, and as a summary for this presentation, we have demonstrated a retrofit of a VRT vacuum furnace with an IGBT MFDC power supply. We observed a 40% lower power consumption in kilowatts, a 14% lower peak demand, and a displacement power factor of near unity across the entire cycle. This correlates to real cost savings for furnace applications. Some of the other things that I did not touch on in this presentation are other forms of savings by using an IGBT MFDC system. These are decreased size of breakers, feed wires, and distribution transformers in the facility. Thank you very much for joining me today. You can find us at www.romanmfg.com, or you can visit our booth at FNA.